I hate this microphone. What can I do? All right, we're getting towards the business end of OpenMP now. Today is the last day of OpenMP, and last week was the first week. So actually OpenMP, you've already discovered, is quite a simple thing to use. Most of it is all compiler pragma directives. Next week we're doing AVX, and then we're finishing up on AVX. All right, we're getting towards the business. Let's do it, shall we? If my thing works. Today is the last day of OpenMP. Come on, computer. And last week was the first week. So actually, OpenMP. All right, we're getting towards the business end of OpenMP now. Before I get too far ahead of myself, last week's tutorial. Now, last week your tutorial was to parallelize that boxcar filter, which was a simple filter for smoothing out experimental data or just smoothing out data. Here's the source code. You didn't have to write it so beautifully. A lot of people wrote some very nice source code to smooth over maybe data from a file. Last week, the only mission was to really verify that these 10 elements were smoothed correctly because I gave you the answer to these. So it's a way of debugging. So that's what the CPU code looks like. That's for your reference. The OpenMP, there we are. OpenMP code that I wrote looks like this. So let's go over it bit by bit. Most of this you guys got pretty well. The very first thing we need to do is set the number of threads. If you recall, at the end of last week's class, I explicitly told you to use 2 OpenMP threads to parallelize the work. If you forget to write OpenMP set number threads, how many threads were you using on my machine? Do you guys remember? 32. Yep. By default, my server, the one that you're using for this class, has the environment variable, the OpenMP number of threads, set at 32. So if you forget to add this, you're going to get 32 threads here and you can get a segfault, which happens all the time. So don't forget to set the number of threads. After that, we create our parallel section. Now, after this, you guys are familiar now with the idea of private and shared variables. Private variable means that extra copies of that variable are made in memory and then shared, well not shared, sorry, explicitly given for each thread to manage. So if I make a variable private and I have 2 threads, let's say I made A private, I make another 2 copies of this array A and share them to the thread indices. But the biggest problem is if I make this private, the computer then creates 2 new copies of A, but it doesn't copy A over into those arrays. So that array A is going to be filled with garbage. So in this case, I don't specify what is shared and what is private. On my computer system, they are shared by default. So because I didn't say that A is shared or AS is shared, the computer already knows. It's by default shared. We'll talk a little bit about this later, but that's okay. So here we jump into parallel mode. After this bracket here, everything between this bracket and this bracket falls into the scope of our parallel computing section, and we create 2 threads to complete this work. Now, if you remember, our mission was to manually parallelize that work, which means that we need to do a few things. If we want to manually parallelize that work, we need to have each thread understand what its thread ID is, and we also need to define some local variables. Now, variables I, j, and tid are used in this computation process. I is a global index to our array, just like the I that we used in GPU computing. J is the local index over our half array, TID is the third ID. All of these are private variables. TID, the thread ID, can't be shared by other threads. If it is, it means each thread is going to be horribly confused about who he is. And so we can't use a shared value for TID. I declare I, j, and TID in this scope, which makes them automatically private. Now there's another I here. Now when I leave this I out here and I don't say if it's shared or private, what is that I? Shared by default. But I've declared a new I here. So between this bracket and this bracket, everywhere I refer to as I in this section of code, we're going to use the local value, not the shared global value, because we take preference for locally declared scoped variables first. So these are private because they're declared within this scope. TID being private, we need to call OpenMP get thread number to understand its ID, to get its thread ID. Once we've got our thread IDs, then we need to execute a for loop. We had n elements, we have 2 threads. We need to share those n elements across those 2 threads. So use a for loop with n over 2 elements in each loop. This is annoying to do, right? Because if I change this to 3, I need to make this 3, and then n might not be evenly divisible by 3. It's not a very fantastic way to do this coding. In fact, there are only certain times that we want to manually share this work. Next week, we will be focusing on a very strong reason for manually sharing this work, and that is for using AVX intrinsic functions together with OpenMP to accelerate our calculations. Today, we're going to find a way to make this parallel without changing this for statement. But back to it, we're manually performing the parallelization. Before, we had one thread exercising across all 10 elements. Now we want each thread exercising across half of those. We need to know where our global index is for each thread, and that's our formula there. This is the same formula as we used in GPU. Basically, that's like a block size. That's our local element. That's our thread ID. The rest is identical to our CPU code. And this is actually the point I want to make, because many of you wrote special sections for this computational work. Normally, when we write a serial code and then we want to parallelize it, this serial code could be quite large and quite complex and difficult to write. If we want to make this parallel using OpenMP, we don't necessarily want to change that code because we spend a lot of time developing that serial code. We can see here, this is the serial code that I took from the serial version, one core. This is the parallel code. This is the actual workload that we perform. The codes are the same. Can you see that? Yeah. Now, when we use OpenMP for parallelization, our mission is to try to keep our parallel code as close to our serial code as we can. Otherwise, if we're going to go to a lot of effort to change our code to make it run faster, we'll just use GPU. If we have a GPU. And they're cheap. They're pretty easy to use. So anyway, the mission is we want to try to modify our source codes as little as possible to make them run in parallel. And I've done that here. So to make my serial code into an OpenMP parallel code, all I had to do was change a few things. I definitely need to do that. Don't forget to set the number of threads, otherwise you will use 32 by default on my server. Maybe on your server it will be different. We need to call that and we need to reconstruct this. It's quite annoying actually. Some of you surprised me last week. So even though I asked you to use 2 OpenMP threads, some of you attempted to do the parallelization like you would on a GPU, and it worked. You all know who you are. I'm not going to point anyone out. More than one person did, and that's fine. So here is my, hang on, that's not mine. What did I do for my one? Oh, I've copied the wrong image across. Actually, I've written that code. I'll change my notes and include that one because I saw so many people doing it. I wrote another copy of the code just to do that. What people were doing were that they were creating, this array has n elements, 10 elements. They were creating n threads, n OpenMP threads, and asking each OpenMP thread to look at one of these elements of A. And so that destroyed this for loop. There's no for loop because it's just like we did in parallelization for GPU. Each thread manages one part. It's a terrible idea. And the reason is because the CPU and the GPU architectures are completely different. And what do I mean by this? GPU is designed to do one thing. What's a GPU good for? Why do you buy a GPU? Hey Paul, why would you go buy a GTX 1080 Ti? And the reason is because Battlefield 4, Witcher 3, a computer game. Yeah. This is why we buy GPUs. You buy GPUs to draw. Those GPUs contain thousands of streaming cores. Those streaming cores are designed to do one thing, draw a picture on the screen. And they are excellent at it. They suck at everything else. That's what they're designed to do. They're designed to perform the same computation across all of the thousands of cores, and they're simple computations, which means that GPU cores are not powerful cores. They're actually quite weak. They do not have large amounts of cache. Remember, each SMP, each streaming multiprocessor has 64 KB of cache. That's a very small amount, considering that the most recent Xeon cores have 24 meg of cache, which is a lot larger. You can even get larger than that nowadays. So the GPU, the threads are what we call lightweight. They're easy to create, they're designed to perform low work, and the GPU is designed to allocate and execute millions of threads at once. The CPU core is nothing like the GPU core. Each core on the GPU is weak, has a small amount of cache and is not very clever. The core on your CPU, each complete core is very, very clever. They all have their own memory fetch instructions and controllers. They all have schedules. They all have their own cache, multiple layers of cache, and they're much larger than the CPU cores. These cores are designed to perform MIMD parallelization work. These are designed to perform SIMD. This is a device designed to handle thousands of cores. When we're using a CPU, we should never try to use too many more threads than we have cores available. That's what we should try to do. So our mission is actually quite simple. We want to, when we pass work to a CPU, we want to make sure that the work we give to the CPU is well suited for the CPU. It takes advantage of the technology that's in the CPU. Modern CPU cores all use AVX, and the newest Skylake X CPUs use AVX 512. This is a feature that we'll be looking at next week, and it is a very powerful tool for accelerating our computation. AVX is basically a parallel computer inside each core. So when we look at this, you see 4 cores here, right? Inside each core there's a parallel computing register that allows us to perform parallel computing in each core. So we have 2 levels of parallel computing that we're capable of performing. When we perform OpenMP, we can actually add more parallelization on top of that by using the AVX parallel registers in each core. That's next week. We want to use AVX. I promise you, every computer game that you've ever played takes advantage of AVX. And half the time, if you try to run a modern computer game on an AMD core, the reason it crashes is because there are differences between AMD's AVX and Intel's AVX. Secondly, these cores are powerful beasts. You want to keep them loaded with a lot of work. So load them up. Keep each thread occupied by large amounts of work. So your mission in, let's say you have a finite element simulation with a million cells. Do not create a million OpenMP threads. You want to evenly divide those million elements across each of the cores you have available. You don't want to overload it, because the problem being, creating OpenMP threads takes a lot longer than creating CUDA threads. They're heavier. It takes time, and we're going to talk about this at the end of today's class, actually. All right, today, loop sharing in OpenMP. I'm sorry. I'm sorry because last week's class, this work, using manual parallelization to parallelize a section of code is not the way that we normally parallelize work in OpenMP. The reason I show you this is because if you want to use AVX, you have to manually parallelize it. If you want to use AVX properly, you have to. But if you're not planning on using AVX, or if you trust the compiler to help you do AVX, then we don't do it this way. FYI, I don't trust the compiler. Neither should you, but we'll get back to that. Today's class. Last week we shared the workload across our elements by manually sharing them. We manually compute the thread ID, we manually tell each thread to do n on 2 elements, and we manually tell each thread where to look. This is an annoying thing to do. It means that we spent a lot of time writing the parallel code. Actually, OpenMP has been around for quite some time now, and sharing work across loops is actually the core component of many engineering and scientific computational codes. So OpenMP is actually designed to help us automatically parallelize this work. It does this by using pragmas, of course, because all of OpenMP is all about pragmas, compiler directives, and OpenMP functions. We're going to use a compiler directive, a pragma, to share this work. So this is a CPU code. It executes from I equals 0 all the way up to n-1 in steps of I++. We're going to do some calculation here. Could be a sparse matrix vector multiplication, could be a dot product, it doesn't matter. If I want to tell OpenMP to automatically share that work, that's what I add. pragma OMP4. After I add that, assuming I already have an OpenMP parallel section out here, OpenMP will automatically parallelize everything inside this for loop. You don't need to change anything. Don't need to change this function. Don't need to change this. Note how this is locally declared. Don't need to change that. Don't need to change anything in here. All I do is that. Now this is quite dangerous because we're asking ourselves to trust the compiler, but this has been around for quite some time now and a lot of people use it, so it's well tested. I can promise you this works. So by taking our for loop and adding pragma OMP4, assuming we already have a parallel section, we can make this run in parallel. Code. Here is a nice easy code to test our crazy idea. What I want to do is create an integer array A. Now, last week, what did we do? Last week we did a filter. Here's our filter. We compute across A, we smooth A to calculate AS. That's our smoothed A, that's why I called it AS. And we save our result. We understand which thread is doing which work here because we manually did it. We know that thread 0 is going to do 0, 1, 2, 3, 4, and thread 1 is going to do 5, 6, 7, 8, 9. We designed it this way. But when we do it automatically, how do I know which thread does which work? You can't possibly, right? You can't predict it, or there are ways we can predict it, but if we want to check to see who is doing what, we can create an integer array, A. We're going to have a constant int n12, so we're going to have 12 elements in our array. A, they're integers, not floats. We're going to have 4 threads, so we're going to set the number of threads to 4. We're going to automatically share this loop, and instead of performing computation, all we're going to do is investigate what thread is executing that part of the array. If this was serial, the answer would be 0, right? 0, 0, 0, 0, 0. In this case, we want to know, if we make this run in parallel, what will our answer be? All right, log into the server and show me. Log into the server, write that code. Run it and show me. You already know the answer because it's right there. But I want you to practice it because we're going to modify this code later to do some pretty useful things. All right. In this case, we want to know if we make this run in parallel, what will our answer be? Show me. All right. You already know the answer because it's right there. But log into the server, write that because we're going to modify this code later to do some pretty useful things. You already know the answer because it's right there. But I want you to practice it because we're going to modify this code later to do some pretty useful things. What will our answer be? All right. You already know the answer because it's right there. But log into the server, write that code, run it and show me. All right. You already know the answer because it's right there. But I want you to practice it because we're going to modify this code later to do some pretty useful things. You already know the answer because it's right there. All right. But I want you to practice it because we're going to modify this code later to do some pretty useful things. All right. You already know the answer because it's right there. But I want you to practice it because we're going to modify this code later to do some pretty useful things. All right. You already know the answer because it's right there. But I want you to practice it because we're going to modify this code later to do some pretty useful things. You already know the answer because it's right there. All right. Okay. I've given everyone plenty of time to write that code down, and I see that most of you have done it. Let's talk about this code for a bit. When you run this code, everyone, this A variable tells you which thread did what work. Sorry, I said that wrongly. That A variable, the TID variable, tells us which thread did which work. 其实这个蛮好用的. It's a very useful tool for seeing which thread did which work. However, 你觉得用这个方式做那个平行计算是一个好方式吗? This A variable tells you which thread did what. It is actually a pretty nice way, and in fact, it's not so much different to the way we just did it, but there is one big problem. Here we have 12 elements, 4 threads. Each one did 3 elements. We can see that 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3. Even line them up for us. Isn't that nice? It even went from thread 0 to thread 3. Does that mean that thread 0 is faster than thread 1? No way, man. In fact, by using this technique, we have no way of knowing if thread 0 is faster than thread 1, or if thread 1 is faster than thread 2, or thread 2 is faster than thread 3. By using the code that we write here, we are telling the computer, hey computer, Mr. Computer, we have 12 elements, 4 cores. You are going to share that work evenly, and you're going to do it right, and you're not going to worry about who goes faster than who. Looking at this result, if this core, this CPU core, he might be busy doing something else. Maybe someone else is using my server to play Witcher 3, which is not likely because it's a Linux box, so you can't use that machine to play games easily, but it can be done. Maybe this thread is busy, but our code doesn't care. We told the code to share the work evenly, and it did. Even if this core is busy doing other things, all of these other 3 cores will do their work and then wait until this core has finished its work. So maybe this CPU gets to this work and then does it, but these ones get there first, and then most of the time while this guy is busy doing this, these 3 cores are doing nothing. They're just idle, doing something else, not work. By writing this code, the largest weakness we have is that we are forcing the cores to do the work in the correct order and fairly, but it is not going to guarantee that our code runs faster. If I want to modify my filter, oh man, is this easy now. So I take my filter CPU code and I add like 2 or 3 lines and I'm done. Here is my for loop. Remember, that is actually my serial code. Everything is a sequential code. All I had to do was add this, 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 and this. I didn't touch anything else. So I've managed to take my sequential smoothing code, my filter, my boxcar filter code, and add 3 or 4 lines. This pragma, that pragma. Set the number of threads. Don't forget to do this or you're going to have a bad day because you'll use too many threads. In the case of my machine. And then you're done. You don't have to change this for loop. You don't have to change any of the if statements inside. You don't have to change anything. We're finished. Using these pragmas, using pragma OMP4 around our for loops is an excellent and convenient way of automatically sharing our loops across our OpenMP threads, but it comes with a risk. If one of our OpenMP cores, well, one of our threads is given to a slow CPU core, it sucks because all of the other threads are going to have to wait for that core to be ready before the program can continue. Nothing here tells the CPU that it should, well, ideally what would we like to do? We'd like to tell the CPU, hey CPU, if this core is busy, don't give work to that core. That's what we'd like to do. And there is a way that we can schedule work in such a way that the work will lean towards the faster CPUs instead of going towards the slower ones. By using this code, we're automatically parallelizing evenly across all of our threads, but there's no guarantee that those cores will be fast. Here's a comparison. Zorbian, on the left is our serial code, the sequential code. On the right is our parallel code. You go to an international conference on parallel computing and people present OpenMP parallelization. There is no work here. To go from this sequential code to this OpenMP parallel code, how long do you think it took me? Seriously, I've got 2 kids. The 3rd floor of our house has 4 kids. The 4th floor has 2 kids. The 5th floor has 2 kids. all the kids are in my house running around crying, screaming, fighting. It still only takes 10 seconds for me to do. It only takes 10 seconds for me to change this code, and then I can start killing kids again. It's not hard work. So the joy, the reason why everyone loves OpenMP, one, it's easy to buy a computer that supports OpenMP computing. That's every computer and every platform. It works on Windows and Linux and every operating system ever created. You can write OpenMP to run on a mobile phone, on an Apple device. The code doesn't change. It's identical. What changes is how you make it run on that. So you need a different IDE to compile and run it. But the code doesn't change. Unfortunately, this kind of implementation is far too simple for us. Next week, I'm going to show you how to use AVX to speed up these kind of calculations even faster. And it is a substantial increase, 8 to 16 times performance increase over this code. But before we do that, we need to find a better way to share this work, because by using Pragma OMP4, we're asking the CPU to share the work evenly across our OpenMP cores, and this is dangerous because you might pass work to a slow CPU core. It wasn't hard. There it is. The code hasn't changed. So by using Pragma OMP4, we can take a serial code and parallelize it very quickly. This is not the last thing you do. This is normally the first step. Then we play with it. Now, if we want to make this analysis a little bit stronger, let's add the same thing that we just did. In the example I gave to you guys, we create a variable and then we allocate the thread ID to each variable so that we can track which thread does which work. This is a very good way to see how our loads are balanced. And together with some Linux environment settings, we can use this powerfully to measure our performance on our machines in parallel. I've added TID, thread ID, it's up here. And inside our for loop, we say TID equals OpenMP get thread number. This way we can see which thread does which. When we run this, there are no surprises here. But have a look at this code. This is slightly different to the OpenMP code that I asked you guys to do. Can you guys see the difference? How many cores are we using here? How many OpenMP threads? 3. How many elements in our array? 10. Doesn't this make you feel a little bit nervous? I know, nothing makes you nervous, man. Except women. That makes everyone nervous. You're not alone there. So, we have 3 elements, 3 cores, 10 elements. How are we going to share the work across? Because in the previous instance where you manually parallelize this work, you can't evenly divide the work across all of the cores. In this case, we're just throwing caution into the wind. We're saying, oh, I know that I can't divide 10 by 3. Screw it. Let's do it anyway. Let's put this Pragma OMP4 here, cross our fingers and hope that everything worked. This time it worked. If you're using AVX with an Intel compiler, it might not work. You can get segmentation faults. Be careful here. In this case, we're trusting the compiler to do the right thing. We've got 10 elements 3. You cannot divide 10 by 3 evenly. There's always one left over. In this case, we use Pragma OMP4 like we don't care. Everything else is the same. Thread 0 has taken on 1 more element. You can see that. Thread 0 does 1, 2, 3, 4 elements. The other ones do 1, 2, 3, 1, 2, 3. So 3 plus 3 plus 4 is 10. Nothing's been forgotten. No segmentation faults. Using the Intel compiler with AVX, you will get segmentation faults, which is a good reason not to use the Intel compiler, but there's nothing you can do about that for some devices. Everything worked here. So what does this tell us? It tells us that using the GCC compiler and without using AVX, we do not need to worry that 10 is not evenly divisible by 3. We can take any problem size, n, and safely divide it across p processors. You can see here that I actually engage and perform a test to see which elements are computed by which thread. I would advise that you do this, because if there is a bug and there is a segmentation fault, it might not be your fault, it might be the compiler's fault. It is a very nice idea to check to make sure everything is going the way it should, because shit happens. And you guys have had experience with this on the GPU. In this case, the OpenMP has done its best to distribute the workload evenly. 433 is the best you're going to get. But it's still not good enough. While evenly sharing the workload might seem like a good idea, on average it is, but most cases in practice it is not. In this case, we use 3 threads. We might assume that each thread is as fast as the others, but in reality, some threads are faster. I don't know why. Students have different speeds. You're made of the same stuff. You're meat and blood. You have more hair than I do, or less. We're about the same with hair. There's not much you can do. But theoretically, we should all be as quick. Same with these CPUs on our systems. You have no way of understanding which CPU is performing which work unless you bind an OpenMP core with an OpenMP thread. And you can bind them. But I'm not going to show you how to do that because that requires modification of the system variables in Linux, which I'm not going to tell you about. In this case, the system will automatically pick cores to manage the OpenMP work, and you will hope that they are equally fast, but they are not. But by forcing an even workload across cores which have different speeds, we are essentially forcing ourselves to go slower because the slower threads will have to force the other threads to wait for them. Unless there is a way that we can provide information to the computer about how to better share the workload. And that is what I'm going to do now. There is a way that we can provide information to the core, to the system, about how we can share these cores, about how we can share the work across these cores. We use the Pragma schedule. So here I've got Pragma on P4. The code that we used before was just Pragma on P4, these ones. This is new. Schedule option option. Option. This is just to show you that there are two magical words that go here. They are not option option. They are actually here. The first one, actually there are several options. There are actually 3 or 4 options, if I'm not mistaken. For the first option, we're going to investigate 2. One is dynamic, the other one is static. Now, static. What does static mean? It doesn't change. It is identical to the code we just wrote. If you write static here, it's basically almost the same as not including any of this information. So why do we have this option? Debugging. Forcing, yes. With regards to AVX computation, we want this static. But otherwise for debugging. Dynamic is one way of saying to OpenMP, hey, Mr. OpenMP, do not statically bind our threads to cores, or do not statically bind allocated workloads to cores. You can shift them around. But the problem being is that's not enough information. That's not enough information to provide OpenMP to give it the freedom to allocate work where it's needed. We need one more option. The second option is this chunk. There are actually more options here, but these 2 will do us for now. Chunk is an integer. Now what do these mean? Oh, animations. So, when we have OpenMP computing, one way that we can do our OpenMP parallel computing is by breaking down our large work into smaller pieces of work. 这个你有做过，在 GPU 上我们要跑 GPU 计算的时候 we take our large problem and we divide it into blocks of threads. You remember that? Blocks of work. And then we pass each block off to each SMP, and we use many threads inside each SMP to do the computation. We do the same kind of idea here. We take our large OpenMP computation and we create chunks of work. This chunk of work is going to look at more than one element in an array if we're doing an array computation. And we say, okay, CPUs, in this case we have 2. You have to manage each chunk of work. If we use static allocation, and we have 6 chunks here, we're going to allocate the same amount of work to each CPU core. This is a stupid idea. Because if CPU 1 is busy helping someone play Witcher 3, it's going to take forever to finish. It all depends on how busy it is helping Witcher 3. Dynamic. What dynamic does is dynamic lines up all of these chunks into a queue. The first available CPU takes a chunk of work and does it. Now this means that if CPU 1 is busy helping someone play Witcher 3, don't say League of Legends or Dota, please. Which game do you pay money to play now? What dynamic does is dynamic. Okay. Now this means that CPU 1 Fallout 4, I finished that, I did Brotherhood of Steel. I went the Brotherhood of Steel way. Anyway, in this case, we start the computation with 2 cores. Core 1, even if it's helping someone finish Fallout 4, will take at least 1 chunk. Core 0 will also take 1 chunk. Now, CPU 0 will finish first because CPU 1 is busy playing Fallout 4 or Witcher 3. When this CPU 0 has finished its work, it takes the next chunk. Takes the next chunk of this file. Now, what this essentially means is, if this core is extremely busy, it can spend all of its time doing 1 chunk, while CPU 0 takes all the other chunks. Now, this is still faster than sharing work evenly because you have no way of knowing how busy core 1 is, CPU 1 is. So by using dynamic parallelization, you might unfairly share the workload, but you're going to finish first. You're going to go faster. Ideally, you want no one to be using your server to play Fallout 4, or Witcher 3, or Dota, heaven forbid. If I find out my students are using Dota on my Linux servers, they're going to die. They use Windows, man, don't worry. Playing games in Linux is too hard. Ideally, each core will do the same, but shit happens. Life sucks. One of these cores, whichever one is ready first, will take a new chunk of work. So this is dynamic parallelization. Let's talk about chunks. Chunk is a finite piece of work. It is a small piece of work which is passed to each OpenMP threads. When we're talking about for loops, we want to share a for loop. A chunk is an integer. Chunk tells the compiler how many parts of our for loop, how many integer parts each thread has to manage. So in our code, the variable chunk is an integer. It tells each thread how many pieces of work it has to do in each chunk. So if you give chunk equals 2, that means each OpenMP thread will do 2 elements of our for array before going to fetch more work. If chunk is 1, then it will do 1. We have to be very careful. The idea is that chunks be small enough so that faster threads can get new work. But if your chunk sizes are too small, you spend too much time managing chunk allocation. If chunk sizes are too large, then it's just the same as using static allocation. You want the pieces of work to be small enough to allow the computer to adapt, but if they're too small, you spend too much time doing administration work, bookkeeping. 你真的花了太多时间处理那些 chunk work and allocation. So that's not what you want. Let's talk about how we set this up. So here's the code. Here we have a code which does some real work. Now when I say real work, what do I mean? 10,000 elements in our array. That's not too bad. That's not where the work is. The work is here. Square root. Square root functions are not simple to perform. How do you compute square root in a computer? Now when I say real work, what method do they use to compute square root? Huh? I know, man. It's right there. But how does it work? How does the square root function actually compute the square root? Newton-Raphson. Yep. Fast square roots use a cheating way of doing it. But otherwise we use Newton-Raphson to compute square root. Newton-Raphson, is that a simple thing? It takes iteration. Now, for a square root computation, Newton-Raphson is very fast because we have a nice curve which is easy to predict and converges very fastly. So Newton-Raphson compute the answer in 3 or 4 iterations. But we're still performing quite a large amount of work here. We're not talking 1 or 2 flops, we're talking 50 flops per square root computation. So we don't use square roots lightly. So over 10,000 elements with this many square roots, if we really want to make it big, add an exponent or an error function calculation as well as the square root here. The exp function is also quite complex because that's a series. So, in this code, we have our for loop. We're computing A, so we are doing some work. 为什么要写做一些工作？以前我们没有做什么工作，我们现在看一下那个 TID 是什么。In this case, we're doing work because maybe later you guys will want to measure the performance. If you want to measure the computational performance, you actually need to give it some real work. Otherwise, the answer is returned too quickly and you can't trust the timing. If your computation takes less than 200 milliseconds to complete, you cannot trust the clock time. You can only trust your clock time if you're measuring computational performance, if your simulations run on the order of a second or up. Otherwise, don't trust the system clock, or wall clock even. So here we go. What does this code actually do? So we compute the square root across each one. That's nice. We also compute a floating fraction. This fraction tells us the fraction of work performed by each thread. So we have p threads here, 4. So our fraction has 4 elements. I set each one to 0, and then I record which thread does which work and increment it. Then if I want to compute the fraction, I divide it by n later. So when I run this code, we're going to compute that problem. We're going to solve the square root of I from 0 up to 10,000. We're going to see which core does which work and how the work is allocated. 如果我们这里写 static, 我们就是公平分享. We share the work evenly. But this case, we're using dynamic and we're setting a chunk size. So we expect that some threads are going to go faster than others. And I'm curious to see which threads are faster. Now, when you run this code, your answer is going to be different to my answer. It's going to be different to everyone else's answer. You're running at the same time. They're binding on different physical cores. There's no way for you to know which core's doing which work because I've disabled thread affinity for this class. So that means that you've got 16 physical cores on that machine, 32 threads. You could be running on any core, but there's no way of understanding which physical core each of your codes are going to be running on. You can't control that. That's a system thing unless I bind the threads, unless I affiliate them, which I haven't done. So your fractions are all going to be different. When I run this code, I get this. This code does two things. You can see I print two things here. First of all, I print a. So a is our square root of I from I equals 0 to n minus 1. Why do I print I? I want to make sure that my calculation works. Because what's the point of measuring parallel performance if I get the wrong answer? People still do this at conferences. They use bugged codes to measure parallel performance. There isn't any point. You want to make sure your code works before you measure its parallel performance. So I only print the first 4, but I'm pretty confident that if the first 4 are correct, the rest are probably going to be okay. You can go and print all of them out if you want to. But apart from that, I print out the fractions performed by each core. In this case, you can see the work managed to thread 0 is about twice as fast as the other cores. It is much more capable. Thread 0 has taken on double the work of threads 1, 2, and 3. So the 30%, 38%, almost 40% of the computational workload has gone to thread 0. Thread 1, 2, and 3 have taken on about 20% each. Ideally, it would be 25, 25, 25, 25. In a perfect world where there are unicorns running outside and PM 2.5 is 0 and everyone's rich and no one needs to worry about money or love, which is a double-edged sword, really. So you can see it's fast. If I change it to static, let's talk about chunk size first. I'm going to change it to static. Now, what's my chunk size? This is important here. 10,000 elements. I use a chunk size of 100. Now what does this mean? It means that I have a for loop here. There are 10,000 parts in my for loop. This for loop iterates over 10,000 elements. Each core, one of these cores, is going to take 100 of these loops. When it's completed its 100 loops, it will go back and grab another 100 loops. By doing this, the slower cores are able to work on their 100 loops slowly, while faster cores are able to grab more and more 100 loop bits, 100 loop chunks of work. Now, if this chunk size was, well, let's see, we have 10,000 elements here. If we share the work evenly, then this will be 10,000 divided by 4 would be 2,500, right? If I made this chunk 2,500, that is identical to making my workload static. Each core has time to get one chunk, and each chunk is 2,500 bits. There's no point in doing it. If I were to make this chunk 1, which is something someone might do, I'm looking at you, that's right. Making a chunk size 1 means every time it completes one loop, the thread will go back and grab one more loop, which means that the thread spends more time going back and getting loop information than doing actual work, which is a waste of time. That's bad. So I need to pick a number which is large enough for each thread to be busy for a while still being small enough so that the threads can respond to work imbalances. So setting chunk equal to 250 would be a waste of time. Hey, I've got a secret for you guys. Do you want to know my secret? So I need to pick a number which is large enough for each information to be busy for a while, which is a waste while still being small. Typing define chunk 5. So I need to pick a number which doesn't work. So setting chunk equal to 250 be careful. Pass it a variable. OpenMP is very funny that way. Well, depending on your compiler. So you can see I've actually created a const int chunk equals 100. What each in your share goals actually define P for define N 10,000. Define chunk 5 or define chunk eBay. If you do, you'll find yourself finding situations where the code doesn't run the way you think it will, because the compiler does not appreciate being passed that information in text. It likes the variable. Depending on your compiler. So if chunk is too large, it means that your program is not responsive enough. If chunk is too small, then it means we spend too much time. Please go ahead and copy this code down and run it for me. I want to see how your computers share that workload. I want to see if it's 25, 25, 25, 25, or I want to see if your thread zeros are faster. I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. I want to see how your computers share. Please go ahead and copy this code down. If it's 25, 25, and run it for me. I want to see how your I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. I want to see if your thread zeros are faster. I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. Run it for me. I want to see how your computers share that workload. I want to see if it's 25, 25, 25, 25. Let's check it out. I want to see if your thread zeros are faster. I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. I want to see if your thread zeros are faster. I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. Run it for me. I want to see if your thread zeros are faster. I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. I want to see if your thread zeros are faster. I'm pretty sure most of your thread zeros will be faster. That's the way the computers are designed. Let's check it out. Back to the microphone, my beloved microphone. I hope the people in Taipei can hear me. That's the reason we're using this damn microphone. Otherwise, if it was just this classroom, then we wouldn't need it. Let's continue. So, you guys have all written this code, and I'm hoping all the students off campus, in your labs in Taida and Tsinghua and wherever you are, have finished writing your code on the server and have actually made it run, and you can see that each time you run it, you get a different result. Different threads do different amounts of work each time you run the code. Using scheduling, dynamic scheduling with chunk sizes, it's impossible to know which thread is going to do which work at runtime, because it's dynamic. This is the reason why when you create your OpenMP code, you be very careful about which assumptions you make regarding which thread does which work, because it is very likely that you are unable to predict which core is going to perform which work, because every time you ran that code, you get a different fraction. Sometimes some threads do zero work, but on average you should see that each thread does about the same amount of work, on average. But you need a lot of work before that happens. Now, one last thing before we move on. If you change this schedule here from dynamic to static, do it now and see what happens. You should see that it changes from some random fraction to 0.25. We essentially force it to use static scheduling. We're essentially forcing each thread to do the same amount of work by doing this. So check it out now, run it now, compile it, show me. I want to see everyone get 0.25. We essentially force it to use. You should see that it changes from some random fraction to 0.25. Man, what is your code doing? We essentially force it to use static compile it. Show me. Essentially forcing each thread. I want to see everyone because it doesn't do all the work by doing this. So check it out now. Run it now. It bailed on some of the elements. That's what it looks like to me. I want to see everyone get 0.25. By changing that to static, you're essentially making it statically allocated. Each thread does the same work, and this is a great way to debug your code. Oh yeah, it's not doing all the work. Yeah. All right. This is the part where we kick ass. Nested loops. In our engineering computations, we rarely write codes which parallelize. You're broken. I don't know what your code is doing. I blame you. In engineering codes, we rarely use one loop. Every time we do a sparse matrix vector multiply, we're talking nested loops. When we're running, what else? Finite time or finite differences, finite elements, we're all using nested loops. Loops within loops. We still need to parallelize these, but we need to be very careful about how we do so. There are two ways that we can parallelize nested loops. I'm going to show you both. They both give you the same result. So the correct parallelization, I'm only going to discuss correct parallelizations here. I'm going to show you two different methods for parallelizing nested loops. One of them will give you the correct answer but will give you terrible performance. The other one will also give you the correct answer but will give you excellent performance. Obviously, the way we're going to try to do it is to have excellent performance, but this is going to come at a cost, and you're going to go crazy. Now, engineering computations, most of the time when I'm talking about nested loops, I'm talking about a time loop and a space loop. Now, we all know very well, can you parallelize time? We cannot. You can't parallelize time. Time is a sequential operation. So you cannot take a computation that requires a previous result and then parallelize this. If your new computation depends on a previous result, it is a sequential operation. And all of our computations in time are explicit, normally, which means that they require an existing result from a previous time in order to compute the new result. So time is not parallelizable. We've talked about this before, though, when we did our finite difference computations for PDEs on the GPU. We can parallelize space. So in our space operations, we can parallelize that if we're careful, but we cannot parallelize time. So in this case, if you recall all of our finite difference methods that we investigated before, we parallelized the inner loop because the inner loop was space. The outer loop was time. let's talk about this. Here is the method. This is like a finite difference computation, actually. We have two for loops. This is a time loop. This is a space loop. We need to complete this loop before we can move on to the next time level. So we cannot parallelize this loop. We must complete this work first. Now we have two options here. We have two parallelization options. When I say parallelization, I don't say that we can parallelize time. What I'm talking about is when we create our parallel threads. So when we create our parallel threads, we can create our threads anywhere in the code. I don't say that we can parallelize time, but I do mean that we can create our threads outside that time loop. But I don't say that we can parallelize time. We have two options. We can create our parallel threads inside, around the outer loop, sorry, the inner loop, or around both. So we can create threads and parallelize calculation on each iteration. So that means prior to our computation here, we create our OpenMP threads, and we share this computation here across our n elements. Then once this computation is complete, we destroy the threads. Now this is fine in practice. But the problem being, at the first time level, we come here, we parallelize our section, we create our OpenMP threads, we share the computation, we complete our work, we destroy the threads, we go to the next time level. Then we create our OpenMP threads again, do our parallel computation, then we destroy our threads again. Creating threads in OpenMP is expensive business. It is not free. If we create our threads inside this section here, before we get to this loop, and we create them and destroy them this many times, that means we're adding substantial computational workload into our code. We do not want this. The other method is that we create our threads here. Now, I do not say that we're parallelizing time. All I'm saying is that we have threads working together to parallelize this section, but stepping through time together. It is quite a complex concept. Let's look at some code. So, code. Now, this is not the complete code. 所以，请你不要跟我说哦，老师那个你忘记写那个 include st.h， 我也忘记写那个 int main， 拜托你可以自己放进去吧。This is the work part. This is the sucky way to do it. Please do not copy this code because it is a crap way. Create our loops here. Create our parallel section here. Create our pragma on P4 here. Scheduling and chunks you can do on your own. We parallelize this. Then we end our parallel section and we do it t times. So you can see here we've got t loops. Each loop we create our threads, do our parallel work, and then destroy our threads. This is extremely slow. This is probably slower than a serial code. We can probably go faster by not using OpenMP at all. Very bad way to do it. But people still do it this way. The only time it would be worth doing is if n is extremely large or calculation is extremely intensive. But even then I wouldn't do it. What we need to do is parallelize the outer block. We create our parallel threads here once. We create threads once. Then we have a for loop here. And then we use pragma on P4 around the inner loop. 你完全不可以放那个 pragma on P4 在这里。You cannot parallelize that outer loop, but you can parallelize the inner loop. Now, what does this mean? It means that from this point here to this point here, we have many threads doing our computation. They are all doing this outer for loop, but we are sharing the work across this inner loop. They are all replicating the work in the outer loop, but there is a danger here. It's not easy to see. Do you think there is a chance that one of these threads might be able to progress faster in time than the other threads? There is a real risk that that can happen. It is possible, since we create threads here before our time computation, that some threads are going to be able to progress through this outer loop faster than other threads, which means that the time synchronization for our calculation is going to be wrong. This is a dangerous risk, but there's something here that you can't see that prevents that from happening in this code. What you can't see here is that every time we call pragma on P4 and we have a for loop, At the end of this for loop, there is a hidden synchronization barrier between our OpenMP threads. So that means our threads are going to synchronize after this. If we do not want our threads to synchronize, we need to put no wait at the end here, which I haven't shown you, just as well, because with that, with no wait here, we would screw our computation. Let's talk about this in a bit more detail. Approach 2, we only create threads once. We destroy threads once. This is the way to do OpenMP parallelization if we have nested loops. Never create threads and destroy threads willy-nilly. Have you guys heard that phrase willy-nilly in English? You don't count. You don't count. I'm just wondering where they would learn it. From me, I guess. Be careful how you perform your parallelization. We want to only allocate threads, create threads and destroy threads once. We do this at the beginning, at the end. If we're using a distributed memory parallelization method like MPI, we do this at the very beginning of the code. We create our threads and destroy them as the first step and the last step in our function. The danger here, we just talked about it, synchronization. The outer loop can become unsynchronized. The only reason that code will stay synchronized is because there's a barrier at the end of your Pragma on P4 that you can't see. If you want to remove it, then you need to add no wait. Yeah. To prevent the error, we need to make sure each thread waits for the other threads before continuing each iteration of the outer loop. We use a barrier to do this. It plays the same role as sync threads or sync device did in CUDA. If we want to chuck it in, it looks like this. If we want to manually add it, you type Pragma on P barrier anywhere in your code. That inserts basically what we like to say is a red light. All the threads will wait there until all the threads are ready. Is this a good idea? Barriers slow your code down. The reason I say you can add no wait to that Pragma on P4 is because barriers slow your parallel code down. It's inevitable. It's like saying that, red lights on the street slow traffic. They do. By moving traffic in blocks forward, you're able to synchronize your time computations, but at the cost of parallel efficiency. The reason we don't need to add Pragma on P barrier to this code is because there is a hidden Pragma on P barrier located at the end of each loop which has a Pragma on P4 in front of it. If you don't want to use that barrier, then after you write Pragma on P4, after that you can write NOWAIT, no wait. It will remove that hidden barrier, and then you can see what happens when you run your code. If I want to manually include my barrier, there it is, Pragma on P barrier. It will not influence the outcome of this computation because this Pragma on P4 has a barrier. No wait. NOWAIT will remove that barrier because you've got this barrier. Why would you do that? Because sometimes there are multiple loops inside this nested loop. You can do those safely in parallel, which means you do not need to synchronize. So sometimes you can perform the parallelization in different loops out of sync, which is safe, and you only need one Pragma on P barrier that is normally at the very end before you go to the next outer loop level. This is a kind of problem that you can get. So, this is a solution to the diffusion equation using FTCS, finite difference method. The black line is the correct solution. Now, I have two codes here. The black line code is the correct solution. The code that generates the red and the blue line is one code, but in that code I do not have a barrier between my time iterations. What that basically allows me to do is allows that some threads progress through time faster than others. It's very dangerous, you can see. Looks like the answers are the same here, and they even look kind of sensible, don't they? This looks like it might be a solution to the diffusion equation. It is not the correct solution. The black line is the correct solution. And you can see here the solution generated differs. By failing to synchronize the outer loop, you introduce unpredictability into your code. Sometimes threads will run faster than each other, sometimes they won't. So that means each time you run your code, there could be a different answer. Generally speaking, if you're running a scientific computation in parallel and you run your code twice and you get a different computed answer each time, you have a synchronization bug. You could have any number of bugs, but one of them might be synchronization. Now, function。我们刚才写一个 variable 叫 frac， 它是给我们看那个 function of work for each core， 那个可以改，那个每次跑那个可以改变，那个是 OK。但是我们算的结果，我们的 finite difference solution 还是怎么样，那个一定是一样的，那个不可以改。如果你算它两次有不同的结果，那你就是完蛋了。Now you know barriers. Now you know OpenMP4, scheduling, dynamic and static. You're pretty much ready. This is actually a real code. If you have a nested loop in time and space, you're going to create your threads out here. You're going to parallelize everything, but you're going to have barriers to make sure time synchronization is maintained. And you're going to use Pragma OMP4 on the internal loops only. The internal loops, the nested loops. You're ready, I think, for today's prac exercise. You already know what today's prac exercise is because you've already got my notes from online. It is a dam break problem. I love the dam break problem because it allows me to use a swear word in class without getting into trouble. Because this dam break problem contains a dam. You guys don't get it. Whatever. I swear anyway. Damn, we're going to remove this wall like magic. And this 10-meter deep water is going to spill over this shallow water, which is only a meter deep. We know what the answer is. And you have the code already. You guys wrote the serial code in week 7 for this method. I gave you the code. I asked you guys to all write it. So you should be able to go onto your server and find the copy of the CPU code that you wrote for this. Right? Eerie silence. If you have already lost your shallow water code or you can't find it, go on to week 7's PPT files and write it again. If you never wrote a CPU code because in week 7 you just wanted to go like crazy and write a GPU code without writing a CPU code, have fun with that. You have two choices. You can download week 7's file and write the CPU codes out properly, or you can change your GPU code into an OpenMP code, which is a horrible activity. I'll just write my CPU code again if I were you. You know what to do. 如果今天, let me tell you, if one person comes to me and says, is my answer right, I'm going to kill them. There's the answer. Don't come and say, oh, 老师, is this water level and speed correct? I will execute you. You've already got a working GPU code. You've got my CPU code. Everyone knows what the answer is. There it is, using the SHLL technique to solve. At least, it is not perfect, but you do get the more or less correct analytical solution to the dam break problem. I want you today to use 5 OpenMP threads with a chunk size of 5 across 200 cells. So your 1D finite volume solver has 200 elements. 5 OpenMP threads, 5 cells per chunk. Compare your result to CPU and your GPU code. You should know that they must be identical. 如果你的 OpenMP code 是跟你的 GPU code 很不一样，那我们有一个问题，因为这个是数学，我们只有一个对的结果。不管我们用平行计算还是一个 core， 我们的结果一定是一样。So check to make sure you get the right answer. Do not ask me if the answer is right. You know what's going to happen. It's going to be blood on the floor. After you're done, you can use the spare time to work on your assignment. Good luck. Yep. So check to make sure you get the right answer. Do not ask me if the answer is right. You know what's going to happen. It's going to be blood on the floor. So check to make sure you get the right answer. Do not ask me if the answer is right. You know what's going to happen. Assignment. It's going to be blood on the floor. After you're done, you can use the spare time to work on your assignment. Good luck. Yep. So check to make sure you get the right answer. Do not ask me if the answer is right. You know what's going to happen. It's going to be blood on the floor. So check to make sure you get the right answer. After you're done, you can use the spare time to work on your assignment. Good luck. After